Hello everyone. Today in this video lecture we are starting a new chapter, that is alcohols, phenols and ethers. In the previous lecture we have gone through alkyl halides and aryl halides. So once we have gone through this haloalkanes, now the next chapter that we are going to discuss is alcohols, phenols and ethers. So we have three topics here: alcohols, phenols and ethers. So we'll take up them separately. So first of all we will take up alcohols. So heading will be alcohols. Now let's define what is the meaning of this term alcohol. Alcohols are a group of organic compounds having OH as a functional group which is attached to an sp3 hybridized carbon atom. So any compound containing OH as a functional group is known as alcohols. Organic compounds containing OH functional group are known as alcohols. So we have to look at this R OH. So here this OH is the functional group. This is the functional group. So this functional group is attached to an alkyl group. So this is what we call as alcohols. So this carbon, this is alkyl group. So when we say this is alkyl group, then this alkyl group carbon must be sp3 hybridized. So an OH functional group which is attached to an sp3 hybridized carbon atom is known as alcohols. Now these alcohols can be classified based on the number of OH groups present in the organic compound. So coming to the classification, first, based on the number of OH groups present. So this is classified as monohydric alcohol. Contains only one OH group. Example, look at this: CH3OH, C2H5OH. So these contains only one OH group. See, these are known as monohydric. Dihydric contains two OH groups. Example, look at this: CH2OH, that is ethylene glycol, so glycols are those compounds containing two OH groups on adjacent carbon atom. So this is glycol. So this OH group is on two adjacent carbon atoms, so we can also say this is vicinal compound, vicinal diols. C, trihydric These contains 3 OH groups. Best example is CH2OH, CHOH, CH2OH, which is a well-known compound known as glycerol. If this contains more than 3, these are known as polyhydric. Many OH groups. Example is, we are looking at this CH2OH, so this contains 6 OH groups. So this is what we call as sorbitol or mannitol. Sorbitol. So this is simply based on how many OH group is present in the given organic compound. So we have monohydric, di, tri, poly, etc. Now these monohydric, the one which contains only one OH group, can be further classified as primary, secondary, tertiary. Monohydric can be further classified as primary if this carbon bearing OH group is attached to only one carbon atom. So look at this. We have CH3, CH2OH. So look at this. This carbon having OH groups is attached to one carbon. So we say this is primary carbon. So if OH is attached to primary carbon, we say this is primary alcohol. Then we have secondary CH3, CH. Now look at this. Carbon having the functional group is attached to two carbon atoms. We say this is secondary carbon, and if OH is attached to secondary carbon, we say this is secondary alcohol. Take this tertiary, we have CH3, CH3, CH3OH. Now carbon having this functional group is attached to 3 other carbon atoms. So this carbon is tertiary and OH group is known as tertiary alcohol. So this is based on the nature of carbon atom having this OH group. If the carbon bearing OH group is attached to one carbon, we say primary. If this is attached to two carbon, we say this is secondary. If this is attached to 3 carbon, then we say this is tertiary alcohol. So apart from this, if we have looked at this type of group, now look at this is not the primary, but this group, look at this, if you look at this group carefully, organic compounds containing this group is known as allyl group, and if OH is on the allylic carbon, we say this is allyl alcohol. Take this group, any organic compound containing this group, this is known as vinyl group, and OH attached to vinylic carbon is known as vinyl alcohol. If the OH is attached to the benzene ring, OH attached to the benzene ring, this is known as phenols. If the OH is attached to the side chain CH2OH, this is alcohol with phenyl as a substituent. So phenyl OH group is attached to this carbon. And this group, organic compound says this group is known as benzyl group. So if OH is attached on the benzylic carbon, we say this is benzyl alcohol. So these are again monohydrate, but the nature of carbon atom difference. Or this is primary, this is also primary, this is also primary, but the nature of carbon difference. So this is how we classify alcohols. So again I am repeating, any compounds containing OH group which is attached to sp3 having this carbon, it is collectively known as alcohols. So this is definition of alcohol, classification of alcohols. Now after this classification, we'll move on to the general methods of preparation of alcohols. General methods of preparation of alcohol. So first we take up preparation from alkenes. So we have the starting compound, that is alkene. Now this alkene is to be converted into alcohol. So let's see how these alkenes can be converted into alcohols from alkenes. Now the conversion of alkene to alcohol, this reaction is known as hydration of alkenes, that is addition of water to alkenes. Hydration of alkenes. The reaction is hydration of alkene. So we have started from this alkene. Alkene reacts with water when this gives you alcohols. So we have looked at this organic compound containing OH group is introduced here. So this is simply addition of water across the double bond of alkene. So we say this is hydration, addition of water to alkenes. This is alcohol, this is alkene, this is the reagent. Now these hydration of alkenes can be carried on different ways. So let's see what are different methods by which this hydration of alkenes can be carried out. So the first method is acid catalyzed addition of alkenes. Acid catalyzed addition. So we have started this alkene reacts with water in presence of concentrated sulfuric acid. So sulfuric acid provides acidic medium. So this is in presence of acid which is known as acid catalyzed. When this gives you if you look at this reaction proceeds via formation. This is electrophilic addition reaction. Reaction proceeds via formation of carbocation intermediate this reaction follows Markovnikov's addition. Markovnikov's rule. So while addition of water to alkenes, in which reaction proceeds by formation of carbocation, reaction follows Markovnikov's addition. Now, whenever we have carbocation as an intermediate, so there is a chances for rearrangement of carbocation to a more stable cation. So when this carbocation rearranges to a more stable, there may be formation of some unexpected abnormal product. Rearrangement of cation. So rearrangement of cation is possible. So whenever there is a rearrangement of cation, rearranged product may be formed. So this is one thing that we have to keep in mind while carrying out this addition of water in presence of catalyst, that is acid catalyst. Look at this example. So we have looked at this CH2 double bond CH2 reacts with water in presence of H plus sign, when this gives you CH3 CH2 OH. CH3 CH double bond CH2 plus H2O in presence of catalyst. So Markovnikov's rule will be followed here. So this gives you 2-propanol. Take this CH3CH. If we carry out this hydration of this compound in presence of catalyst, so first secondary cation formed here, this followed by hydride shift to give you a more stable tertiary cation giving this compound. So this is totally unexpected product. So in this case, first secondary cation is formed which rearranges to a more stable tertiary by hydride shift. In the same way, if we carry down this compound CH3 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 CH double bond CH2, hydration of this compound, when this gives you a methyl group shift here. So these type of unexpected compounds may be formed if reaction is carried out in presence of acid catalyst. So this is one of the methods by which we convert these alkenes to alcohols. The second method by which this addition of water can be carried out, this is known as oxymercuration, demercuration. This reaction, oxymercuration, demercuration, this involves two different steps. First step is oxymercuration reaction followed by demercuration reaction. So two reactions combined together to give you a particular reaction. So for this oxymercuration reaction, the reagent uses mercuric acetate. Mercuric acetate in presence of means water in presence of mercuric acetate. Demercuration step, the reagent used for demercuration step is sodium borohydride NaBH4. So reaction is C double bond C alkene reacts with water first in presence of mercuric acetate followed by reaction with sodium borohydride, when this gives you alcohol, and this reaction oxymercuration demercuration reaction, this reaction follows Markovnikov's addition. The reaction has to follow Markovnikov's addition, no cation formation, so whenever there is no formation of carbocation as an intermediate, the question of rearrangement does not take place. No rearranged product formation. So let me just give you this reaction here. C double bond reacts with water in presence of mercuric acetate when we have this. So the first step is addition of mercury along with water. So these steps, simultaneous addition of water as well as mercuric acetate to the double bond of alkene. This is known as oxymercuration. And in the second step, this is treated with sodium borohydride when this mercury is replaced by H minus coming from this hydride. This is alcohol and this H is coming from this reagent. So this is a reducing agent. So if you look at this reaction from reactants to the product, this is simply addition of water. So this addition of water we carry out by an alternative pathway, that is first oxymercuration followed by demercuration. The second step, this step is demercuration. So this is normal addition, but by use of mercuric acetate and sodium borohydride, in which Markovnikov's rule is followed. There is no cation formation, so no reagent product will be formed. Take this example. CH3, CH, CH3, CH double bond, CH2. If this reacts by this mechanism, that is oxymercuration, demercuration, the reaction will follow Markovnikov's addition. So the product will be CH3CH, CH3, CH, OH, CH3. This is the only product that is formed. CH3, CH3. Take this alcohol. Now this reacts with water in presence of mercuric acetate followed by the reduction so there is no rearrangement of the product, whereas in the previous method there was a rearrangement if we started with this alkene. So this is what we call as oxymercuration, demercuration. The third method by which addition of water can be carried out is hydroboration oxidation reaction. Again, this is a combination of two reactions. First reaction is hydroboration, second reaction is oxidation. Now for this hydroboration state, the reagent used is diborane, that is B2H6 in presence of tetrahydrofuran. Oxidation state, the reagent used for oxidation state is hydrogen peroxide in presence of alkali. The reaction is C double bond force reacts with B2H6 in presence of tetrahydrofuran. When this gives you trialkyl borane. So 1 mole of B2H6 reacts with 3 moles of alkene to give you trialkyl borane. So this addition of boron to alkene, this is known as hydroboration. This is hydroboration step. So in this hydroboration step, boron atom goes to that carbon atom which is least sterically hindered. In the second step, this trialkyl borane is reacted with hydrogen peroxide in presence of alkali, when this B will be replaced by OH group. So this is 3 moles of alcohol plus H3BO3 is formed. So this step is known as oxidation step. So if you look at this starting alkene and the final product, just compare this. Starting from this alkene to this final product, there is simply addition of water, and this addition of water has, this is addition of water, but by different pathway. So by this hydroboration oxidation reaction, the reaction proceeds via a cyclic 4-member transition state. This reaction is anti-Markovnikov's addition. No cation formation, no rearranged product formation. So for a second we take this example. So first we read this way, B2H6 in presence of THF followed by reaction with H2O2 in presence of peroxide. The reaction says this follows anti-Markovnikov's addition of water to double bond of alkene. So therefore the product formed will be this. This is the product formed. Take this alkene, carry out the same reaction, B2H6 in presence of THF alkaline peroxide. The product form is CH3 CH2OH. So this is the difference between these 3 methods: direct addition presence of acid, oxymercuration, demercuration, and hydroboration oxidation reaction. Now I'll combine these 3 in some specific compounds so that you can differentiate between the nature of products formed by these 3 different pathways. So we start with this compound CH3 CH3 CH double bond CH2. Now react with this water in presence of acid catalyst. That is in presence of mercuric acetate followed by reduction with sodium borohydride. First reaction with B2H6 in presence of THF followed by oxidation. So these are three methods by which we can carry the addition of water. The first one, look at this. There is carbocation formation. The reaction is Markovnikov's addition. Rearrangement is there. When the product form is CH3 CH3 OH CH2 CH3. This compound hydration in presence of catalyst, acid catalyst, gives you tertiary alcohol. Take the second reaction, mercuration, demercuration. No cation formation, Markovnikov's addition, no rearrangement. So simply Markovnikov's addition will be there. CH3 CH CH3 CHOH CH3. So if you look at this, this gives you secondary alcohol. The third, that is hydroboration oxidation. CH3 CH CH3 CH2 CH2OH. I can look at this reaction is anti-Markovnikov's addition of water when this gives you primary. So the same alkene can be converted into primary, secondary or tertiary depending on the choice of reagent. Take this alkene again, CH3 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 CH double bond CH2 H2O in presence of catalyst. So first carbocation followed by rearrangement, CH3 COH CH3. So this is totally unexpected product. Markovnikov's addition with no cation formation, no rearrangement here. In the third reaction, anti-Markovnikov's addition with no cation formation. So this is the difference between these three modes of addition of water to alkenes. So this is what we call as hydration of alkenes. So alkenes can be conveniently converted into alcohols by these three methods. So this is the first method by which we can prepare alcohols. Now the second method of preparation of alcohol is via Grignard synthesis, that is by use of Grignard reagent. So let's take up the second method. Grignard reagent, or simply we say this is Grignard synthesis. So the starting compound for this Grignard synthesis, carbonyl compounds of aldehydes and ketones. So this may be aldehyde or this may be ketone. This reacts with RMgX, alkyl magnesium halide. So if you look at this reaction is nucleophilic. Nucleophile electrophile reaction. Look at this. This is carbon with negative charge. This is a very good nucleophile. So this nucleophile attacking electrophilic carbon here. Carbon double bond oxygen. Oxygen being more electronegative, pi electron is withdrawn by oxygen, so carbon becomes electrophile. So this electrophilic carbon is attacked by nucleophilic carbon. When this gives you that is addition product. Now this addition product, either we reacted this with what, H2O, or with any acid where this magnesium is replaced by H. So this alcohol that we get here, this may be primary, this may be secondary, or this may be tertiary. So depending on the choice of aldehyde ketones, we get primary, secondary, or tertiary alcohols by this method. So let's see under which condition we get primary, secondary, and tertiary alcohols. Now suppose if the starting compound is formaldehyde, that is formaldehyde. Now this formaldehyde reacts with RMgX, formaldehyde. So formaldehyde by this Grignard synthesis gives you RCH2O minus MgX plus when this gives RCH2OH, that is primary. If the starting compound for this synthesis is formaldehyde, so formaldehyde will always gives you primary alcohol. Whatever may be the nature of this alkyl group, formaldehyde will always gives you primary alcohol. Take this CH2 double bond O, this reacts with CH3 MgI. So if you look at it, this CH3 attaches here, so we have CH3 CH2OH. Take this reacts with CH3 CH2 MgI. So this is the alkyl group. So a new alkyl group is introduced, that is CH3 CH2 CH2OH. Take this CH3 CH3 MgI. So the alkyl group is CH3 CH2, then CH2OH. So we always end up in getting primary alcohol from this formaldehyde. Now in this method, if any aldehyde other than formaldehyde is used, this is R C double bond O, that is aldehyde other than formaldehyde. This reacts with R prime MgX. When this gives you RCH, so a new alkyl group is introduced here, R prime. When this gives you O MgX, these on reaction with water or H plus ion, this gives you RCH R prime OH. So this is always secondary. So any aldehyde other than formaldehyde, this will give you secondary alcohols. So take this example, CH3 CH double bond O reacts with CH3 MgBr. So the reaction product is CH3 CH CH3 OH. So we get this as a product. So a new alkyl group is introduced here. A react this with CH3, CH2, MgBr. We have the product C2H5, that is the alkyl group that is being introduced here. We have OH, take this react with CH3, CH, CH3, MgBr. So the product is CH3, CH, isopropyl group is introduced here. So in all these, the product is secondary alcohol. But if the starting compound is ketone, then the product will always be tertiary alcohols. So we have R prime double bond O react with MgX. This is ketone. So this always gives you tertiary alcohol. So let's take up this CH3, CCH3, that is acetone, react with CH3MgI, followed by reaction with acid. When we get this CH3C, CH3, CH3OH, that is tertiary alcohol. Take this CH3, C2H5, double bond O, CH3, CH2, MgI. So we have this CH3, C2H5, a new C2H5 is introduced here. So we get this again tertiary alcohol. So take this is ketone, react with CH3, MgI, so we get this. So formaldehyde, primary, any aldehyde other than formaldehyde, secondary with ketone, the product is tertiary. This is Grignard synthesis. It means synthesis by using Grignard reagent. Then the next method of preparation of alcohol is by use of reducing agent. So various organic compounds, means various functional groups, can be reduced by a given set of reducing agents. So I'll give you the list of compounds and the expected product and the reducing agent that could be used for this reaction. By reduction with a reducing agent. So we have look at this. That is aldehydes and ketones can be reduced to alcohols. This is organic acids. So acids again can be reduced to primary alcohols. There is esters. Esters again reduced to a mixture of alcohols primary plus ROH. This may be primary, secondary, tertiary. This is acid halides, again reduced to alcohols. This is again primary. Then we can have acid anhydrides. Again this can be reduced to give you 2 moles of primary acids. So these are the functional groups. We have aldehyde ketones, acids, esters, acid halides or anhydrides. These can all be reduced to the corresponding alcohols. So what are the list of reagents that could be used? Let's see. So first reaction, reduction of aldehyde ketones to alcohols. The choice of reagent, first look at this: lithium, aluminium hydride. Then we have sodium borohydride. Then we have hydrogen in presence of nickel. Then we have B2H6. These are the reagents that could be used for reduction of these compounds. So with this lithium aluminum hydride, this gives you a reaction: sodium borohydride positive, hydrogen positive, B2H6 positive. Then we have acids to give you primary alcohols: lithium aluminum hydride positive. Sodium borohydride does not reduce acids. Hydrogen positive, B2H6 positive. Reduction of esters to a mixture of alcohols. Lithium aluminum hydride reduces esters. Sodium borohydride does not reduce acids and esters to corresponding alcohols. Hydrogen reduces, B2H6 reduces. Then we have look at this: acid halide reduces to alcohol by lithium aluminum hydride, by sodium borohydride, by hydrogen in presence of nickel. Diborane does not reduce acid halides. Then we have look at this: acid anhydrides to corresponding alcohols. So these are the various functional groups. These functional groups can be reduced by these reagents: lithium aluminum hydride, sodium borohydride, hydrogen or diborane. So let me give you some examples of this reduction of various functional groups by reducing agents. So we have CH3, CH double bond O. You have to reduce this by use of any of this reducing agent when this gives you CH3, CH2OH. Take this CH3, CH3 double bond O. By use of any of this reducing agent, we have this CH3, CH3, CHOH. Take this CH3, CH2, C double bond O, OH. So we have to use, except this sodium borohydride, we can use any of this reducing agent when this gives you CH3, CH2, CH2OH. You get CH3, CH double bond, CH, CH2, CH double bond O. So if I reduce with this, lithium aluminum hydride, then this will give you CH3, CH double bond, CH, CH2, CH2, OH. But if I reduce this with hydrogen in presence of nickel, so hydrogen in presence of nickel being a very strong or very powerful reducing agent, all other functional groups present in the organic compound will also be reduced. So along with this C double bond O, we also have a CC double bond. So this CC double bond will also be reduced. So the product is CH3, CH2, 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 CH2OH. So this thing we have to keep in mind. So these are the reduction of various functional groups by use of reducing agents. So by this method we can prepare alcohols from various organic compounds. So this is some general methods by which we can prepare alcohols.